Hi, welcome to this video. In this video, we're going to see how to draw the axial force, shear force, and minimum diagrams of four frames. The first problem, we have two members A, B, and B, C of the frame shown. First, we will determine the support reaction. This is a determinate frame, therefore, we can directly find the support reactions as shown here. After this, we need to construct the free body diagrams for these two members. So first, we will start with the member AB. So when we do that, we make a cut here closest to this joint B, right? So somewhere here maybe. Then we will move on to drawing the free body diagram of member BC. Okay, so we cut the member here and then we see the free body diagram of this member, then we will move on to the other one. That's what we have shown here. This is the support reaction, this is support reaction. And at this location, joint B, that is joint B, these are the internal stress resultants that are required to keep these two members in equilibrium, right? So this 10 kilonewton is nothing but the applied load, this 10 kilonewton, okay? So when we join these two ends, it should remain in equilibrium, okay? We can see that this equilibrate will equilibrate with this and this bending moment equilibrate with the other one. And this 10 kilonewton is nothing but the external load that is given in the actual problem, right? What is the next step? We need to draw directly the SFD BMD and AFD, but mind that the axial force and shear force are defined consistent with the local axis of the member. So as the member is inclined, we see that these support reactions, what we have here, that is 6.34 kilonewton and 10 kilonewton, are not aligned along the axis and normal to the axis of the member, right? Therefore, we need to resolve these two forces. How to resolve this 6.34 kilonewton? This will be resolved like this, okay? So along the axis of the member, it gets resolved like this, and along, normal to the axis of the member, it will be pointing in this direction. How about the other support reaction, 10 kilonewton? This will be resolved in this fashion, right? So for VA, we have this, and for this 6.34 kilonewton, we have this, and then for the 10 kilonewton, we have this. So in the direction along the axis of the member, these two get summed up, and in the direction normal to the axis of the member, they will be they are in the opposite directions. Therefore, one will be negative, and other will be positive. So after resolving it, we directly get the values of NA and VA. Something is missing here. Sorry about that. I should have also shown this presence of shear forces at this cut end as well. Okay, that should be present. So after determining these values, we see that these two values are constants. Therefore, we should have just a rectangular variation because along the axis member, we don't have any other axial or any other force which acts in the axial direction or transverse direction of the member. Therefore, this remains constant. However, this mz varies with respect to x, right? So as x varies from 0 to 2 meters, this is the variation of the bending moment, right? So then we directly depict them, fine. So this is the variation of axial force, this is the variation of shear force. This is positive, so we are drawing it in the positive y direction. This being negative, it's drawn downside the positive y direction. And then finally the bending moment variation, which is a linear variation. Just we see this triangular variation, right? So 3.66 into 2 meter will give the maximum value of 7.32 at the other end. Now we'll move on to the next member BC. We repeat the same steps. That is, we need to resolve this force 6.34 kilonewton, okay, which is there at the joint B. So when we resolve, these are the values we get. And again, apologies, I should have shown these two forces here. Okay, those are the internal stresses, that is shear force and axial force at this cut end. Fine. And again, there will be a linear variation of the bending moment. The maximum value will be 7.32 kilonewton meter. Fine, which is at this end itself. So this is the roller support. For the member BC, this is the roller support. So the bending moment will be 0 here. So the variation will be something like this. Okay. Direction we need to see. It depends on the axis what we have picked up. Mind that we take the x-axis along the axis of the member and y-axis is located 90 degrees counterclockwise from the x-axis, right? So these two are constant values, just negative and positive, and this is the maximum value, but it's a linear variation again. So we see that this is the variation, fine. So once we know these two, we can combine them to show the final variation for the entire beam, entire frame. Okay, that is not shown, however. Anyway, that is trivial. Once we have done up to this, it's straightforward to just combine them and show it, right? We'll move on to the next problem now. Second problem, we have a cantilever frame, okay, with these three forces, concentrated forces acting at the joint D or the free end D. So again, here it is not necessary to determine support reactions if you are going to start from this end. So that's what I'm doing here. Directly I'm starting from this end. So first I'm taking the member DC. I'm going to show the free body diagram for this. Then I will move on to BC. Then I will come to this member AB. Fine. So first we start with this member CD. These are the external loads that are acting here on this member. So at the other end, these three forces, internal stress resultant, should exist to keep the equilibrium. I mean, to maintain the equilibrium of this member CD, right? So 2, 2, 1, 1. This is 3, and then this 2 kilonewton plus 1 into 1 equilibrates with this 3 kilonewton meter. Okay, it's straightforward. One can do that. Then from here to here, when we combine, merge these two ends, they should remain equilibrium, right? So whatever forces you have here, show the same forces in the opposite sense, direction wise. Okay. Then you come to this joint B and see what are the internal stress resistance that are required here to keep this member BC in equilibrium, right? So this 2 kilonewton should be equilibrated by this 2. This 1 kilonewton should be equilibrated by this 1. And how about this value of the bending moment there? So we see that this 2 kilonewton meter bending moment is already there, and then due to this 2 kilonewton, 2 into 2, 4 plus 2, totally 6 kilonewton meter is there, and this is counterclockwise, right? So in order to equilibrate that, there should be a clockwise 6 kilonewton meter bending moment here. So that's the way we get the values that are required to complete the free body diagram of the member AB as well. When we do that automatically, you determine the support reactions here. Okay, you can do either way. You can start from the support reactions and move toward the member D, or you can start from the free end and end with the support reactions. Fine. After that, again, usual procedure, but we need to fix the axes. So I'm starting from this joint A, and then I'm going toward joint D when I mark this local axis. So this is X, counterclockwise 90-degree Y. Then I come to this member BC, this is X, 90-degree counterclockwise Y. And finally, this is my X for the member CD and 90-degree counterclockwise Y, okay, for the member CD, right? Then there remains nothing. You know how to draw this now, okay? So because you have all these values here, right? You know all these values here. Then you can make a cut at every member at some random location, and you can represent the variation of all three internal stress resultants with respect to X. Once you know those expressions, you can depict them the way we have done here. Okay, SFD BMD and then AFD. Just I will show it for, or just I will discuss it for SFD. So for SFD, it is straightforward. That's why I'm taking it directly. We see that in all these cases, the shear force is constant for each of the member, right? Each member. So 1 1, 2 2, and then 1 1. Negative or positive depends on the axis what we have here, right? So here this is the axis we have. This is clockwise, so this should be negative, and this is your x and y, right? So this will be positive because this constitute a counterclockwise pair, and finally this is your x and this is your y, again counterclockwise, so it has to be positive, right? You must be following these details. If you are not able to follow this, you can go back to our last two videos and see how these conventions are used, right? So positive, positive, negative, and just rectangles. This variation you can, for this you need to write the expression for mx for each of this member. Just this linear variation, so there is nothing much to bother. Okay, all will be positive here based on the sign convention what we have. Here, all the bending moments will be drawn on the compression side of the member. That's the only thing I want to emphasize here. and then complete the AFD as usual. Fine. So next one is a bit interesting one. We have a member, okay, we have a frame which is inclined like this, right? So usually we see the cantilever beam like this, but we have a frame here which is configured in this manner, right? So as I told earlier, AFD, SFD are to be constructed consistent with the local axis of the member, right? So I can't have an axis like this and then do. I can do that, but then we will have to resolve the forces, right? So there are two ways. Either you can start with a global axis and then resolve the forces, or you can directly set your axes aligned along the longitudinal axis of the member and normal to it. That's what I'm doing here. So after fixing the axis, I'm going to take this and draw here. Okay. So just I'm rotating this and maintaining it as horizontal and then drawing here. Okay. However, the axis is along the longitudinal axis of the member. That is x-axis along the longitudinal axis of the member, and then y-axis is measured or located 90 degrees counterclockwise as usual, right? So the support reactions, either you can start from the free end and complete the problem, or you can find the support reactions. But here I have determined the support reactions. Anyway, it's not required. You can still finish the AFD, SFD, and BMD if you start from the free end as well, right? So in the local axis, you will have to resolve this force 5 kilonewton, right? So it will be resolved like this. All right, that's what is shown here. Okay, it's once you have done that, there is nothing frightening here because this is just a beam problem now. Okay, you need to draw the AFD, SFD, and BMD for this the way you do it for a beam as usual, right? So this is phi cos 60, which is a compressive force. So this is shown negative here, and then axial force diagram and bending diagram as usual. You can go back to our videos regarding construction of SFD BMD for beams. Okay, so this is the usual procedure. You can construct this ones. Then the last problem is this. We have particularly a constant moment acting as this joint B. That is what is typical in this problem. Okay. So first step is to determine support reactions, get the support reactions. Okay, fine. So this is a determinate problem, determinate frame. So it's not that difficult. Then the local coordinates are shown the way marked here. Okay, so x, x, x. So we consider three members here, AB, BC, and C. Because we have a constant load acting here, therefore it is essential to make a cut here and then consider it as two members, BC and C. Fine. What is the next step? Yes, free body diagram. What we have done here is we started with the member AB, then we went to member BC, then we finally finished with member CD. So when we start for the member AB, we'll start with the support reaction, and then we see what are the forces in terms of resistance required here for the equilibrium of this member AB, then show the same pair here. Okay, but this is tricky here a bit. See, I have particularly shown the joint B. Why they do so? Because establishing the moment equilibrium is little involved here. Because usually if the constant moment is not present at a joint, it's easy. Okay, you don't need to bother much about this joint here. So when we move from this to this portion of these two members, I mean AB and BC, it's helpful to consider this joint B. Okay. So when we move from this to this portion, same forces in the opposite sense are marked 1, 1, right? 1.75, then 1.75. Okay. And then what else? And then you have maybe I think I should have shown this here. Anyway, it doesn't bother, it doesn't matter much. And finally, this 7 is counterclockwise. This should be clockwise 7 kilometer. And additionally, we have this externally applied concentrated moment. Okay. So now when we come to this end, we need to pick these values carefully, right? So we have this 1.75 kilonewton, which must have been here actually. Okay. So this is equilibrated by, yeah, this should be here. Fine. So this equilibrates this diagonal direction. This 1 kilonewton cancels each other. maintaining vertical equilibrium. Finally, for moment equilibrium, I have this counterclockwise 10, this is clockwise 7. So for equilibrium, there should be clockwise 3 kilonewton meter here. Okay, only then equilibrium will be satisfied, moment equilibrium will be satisfied at this joint. So that is the necessity for this joint diagram. Okay, so once you know this is a clockwise 3 kilonewton moment. So when you draw the free body diagram for BC, this counterclockwise, I mean, for this clockwise 3 kilonewton meter, there should be this 3 kilonewton meter counterclockwise moment should be acting here. And this 1.75, 1.75, this one help each other, okay, to maintain equilibrium. Rest of the procedure is one and same. Then we have drawn it for member BC, free body diagram of BC. And then we also consider the joint equilibrium for C because we have considered forces acting here. So it is helpful to consider the joint equilibrium of the joint C as well. This 1 kilonewton and this 1 kilonewton are the external loads, okay, because root 2 is what we have and it is acting at 45 degrees, right? So when we resolve, you get downward 1 kilonewton and rightward 1 kilonewton force acting, right? So that's what is shown here. Downward 1 kilonewton, rightward 1 kilonewton. And this set gives rise to these forces. And finally, for equilibrium, we will need this 0.76 Newton, which anyway is the reactive force there, right? Because there's a roller support there. Fine. All right. So that completes the free body diagrams. And next part is directly drawing the AFD, SFD, and BMD as usual, right? So in this sense, so we require this, at least if we mark this y-axis, that is helpful because just you will have to see whether you need to draw above or below the positive y-axis. So just I am ignoring the x-axis here as it gets messy sometime. And this completes the bending moment diagram. That means this one. All right, hope this helps. You can see there are several problems which one can think of when it comes to frames. This is very limited details or very limited examples what we have discussed here. One can have the presence of internal releases, right? Or one can have linearly varying forces or even nonlinear forces applied on the frames. We are not discussing all of them in detail. In case you require any particular problem to be solved, you can let us know. We will solve it and then publish it here. Okay. Thank you for your patient listening. We will meet again on a different topic. Thank you.